Hello all, and welcome to my Physics 2211 Lab Number 5 presentation by myself, Zakir Ahmedin. So to introduce you to this lab, we can choose any concept, and I chose the supersonic freefall idea. We are going to observe the motion of a man in a free-falling capsule. We're also going to use Newton's second law to predict the position of the object at various times. Then we're going to make comparisons between the experimental data and the computational model. So some key concepts. One is that velocity is equal to the displacement divided by the change in time, where displacement is just the final minus initial position, and the change in time is just going to be the final minus initial time. Also, Newton's second law is another fundamental concept, which states that the net force is equal to the sum of all forces. We have two forces on the system, gravity and drag, and they point in opposite directions. The force of gravity is just mass times the gravitational constant, and the force of drag is equal to b times mv squared, where b is a proportionality constant. Then we also have the velocity update formula. V final is equal to v initial plus F net divided by mass times delta t. And the position update formula. The final position is equal to the initial position plus the average velocity times the change in time. So we have some initial values and assumptions to make this glow script code possible. One is that the mass of the object is equal to 1,360 kilograms, and that motion occurs in the negative y direction solely. So we have no rotational motion, we have no motion in the x direction. And we also have two forces acting upon the object, gravity and the drag force, as mentioned previously. And also that the coefficient for the drag force is 0.028, and this is determined through trial and error in GlowScript. I also found the time where the maximum velocity is achieved through the experimental data, which was 42 seconds. I also assume that air density is constant and temperature has no effect on the drag force. Both of these are somewhat untrue, as air density decreases as elevation increases, and also as temperature increases, the drag force actually increases. But both of these assumptions were needed to be made to be able to develop a computational model, because these relationships are not easily determined formulaically. So I can show you my GlowScript code now. This code was actually very similar to lab number 2 with drag, except we have a change in the proportionality constant, which was determined experimentally. We have a change in the time interval, which was 42 seconds. And we have the gravitational force and the drag force, these formulas that were shown earlier. And then we also have these update formulas, the velocity and position update formulas. And then since this is a loop, we have to advance the clock by adding the delta t to the time and then recalculating all of these values. So I can run the program and show the models. So here we have the velocity versus time graph, and here we have the position versus time graph. So here we can see that the final velocity is actually equal to negative 371 meters per second, which is extremely close to the negative 372 meters per second that was actually achieved during the free fall. And because this was so close, this is how I determined the proportionality constant. I kept trying to run this code with different proportionality constants until I got one that was very close to the actual observed final velocity. And I can actually compare this with the real data. As you can see, these are my two models, and then here we have the Stratos descent experimental data. And we can see that the velocity versus time is also quite linear up until the point of the maximum velocity. And then the position versus time is also quite similar until this point where we have this concave looking graph up until this time interval. T is equal to roughly 42 seconds, which would be about 2/3 of 1 minute. So overall, the capsule's velocity can be modeled computationally, and a proportionality constant b for the drag force can be determined through trial and error. Some variations may exist because d is equal to BV squared is too simplistic of a formula to perfectly model drag force when we have varying uh, temperature as well as varying air density. But among this certain time interval uh, where we are approaching the maximum velocity, it does seem to actually model this fairly well. Thank you for listening to my presentation on lab number 5.